Hello and welcome back to Dissecting Computer Science Lab. In this particular video, we are going to discuss one of the problems in LLMs or any language model, which is the representation problem. And this basically is the very first problem that is addressed before going on further development of such models, which is the representation problem. Now, what exactly is a representation problem? So, human language is actually rich, ambiguous, and symbolic, right? Because it has huge vocabulary, right? And there might be ambiguity in the language, and every word has a specific meaning. Now, machines operates purely on numbers, right? Now, there's a challenge. That is, how do we convert the human language into numeric representation without losing the meaning? It's very important. How do we convert the human language into the numeric representation without actually losing the meaning of the word? This problem actually is the representation problem. That is, how do we represent human language to make it understandable for machines? Now, the fundamental mismatch is human understand words, meanings, and context, right? Humans understand it. What about machines? They just process the numbers and the mathematical operations. They don't understand what we are saying. They can only understand the numbers and can only understand the mathematical formulas and operations. Say, for example, there's a text, I love AI. Now, to a machine, this has no meaning. Right? This is just a sequence of characters with no inherent meaning. So what can we do is how do we make machines understand the meaning of this? The very first thing is because the machines understand numbers, can we have a numeric representation for it? So the basic thing, can we map this to ASCII or Unicodes? So for every characters, we have the corresponding ASCII code or the Unicode, as you see here. Now they have the numeric representation. But then, what is the problem with this? The problem is there is no specific meaning to this particular numbers that we have generated, right? There is no semantic meaning because there is no relationship between the word love and the hate. If I just, just assign them some numerical values without actually having a proper formula or relationship for assigning the values. They are just being assigned based on the ASCII code. Now, this nowhere captures any meaning of the words, no semantic meanings, and they are basically unrelated if in their numerical representation. Okay, so now let's see an attempt two, that is where we will try to assign the token IDs to the token. This is the alternate approach. What we can do is we assign token IDs to each of these tokens, right? Now, which means we're just assigning a random ID to I, love, and AI. What is the problem with this? The problem is these IDs are completely arbitrary. There is no specific rules or any mathematical foundation behind this based on what you're assigning these IDs to them. Why can't I assign 0 to AI, 1 to love, 2 to AI? Or why am I actually assigning 0, 1, 2? Right? Then it can be anything. There's no proper formula or relationship between these, right? So they're completely arbitrary and there's no similarity information present. I mean, just looking at the IDs, you cannot tell which words have similar meaning or different meaning, or whether or not they are similar to each other, right? For example, if I say cat, dog, and car, and if I just give them IDs 5, 6, and 100, right? These numbers do not reflect the semantic relationship. Again, they are just IDs. They don't capture the semantic relationship between each other. The third attempt would be one-hot encoding. This is pretty interesting. What we can do is right now, suppose we have a vocabulary of size 3. We have 3 words in the vocabulary: cat, dog, and car, right? So we have 3 words in the vocabulary. So we have 3 columns. Suppose this is for cat, this is for dog, this is for car, right? Now, if you want to represent cat, okay, with one-hot encoding, we can have 1 here, others will be 0 because this is a cat. For dog, we can have 1 here and others will be 0 because this is a dog. For car, we can have 0 0 here, 1 here because it is a car. It lies under this column, right? It's a one-hot encoding representation. Looks pretty simple and easy, right? But what is the problem? The problem is the high dimensionality, because when your vocabulary size increases, right? Because right now you have only 3. words in the vocabulary. What if I have 50,000 words in the vocabulary? Because GPT actually has around 50,000 words in the vocabulary. In that case, what happens is you'll have a huge matrix there, suppose, right? And just for representing cat, you will have around four. If the vocabulary size is 50,000, then 4999 zeros will be there, isn't it? Everywhere you'll just give zeros, and just at this place you'll be giving one. So it's quite sparse. That's what we say, sparse, because mostly the representation will contain zero, and only one place it will be one. And for this, only this will be one. Others will all be zeros. So unnecessary adding to computation and memory, right? So this again is not a feasible way of representing the numbers into vectors. And again, no similarity captured, right? So how do I say whether cat and dog are similar? I mean, they come under some similarity between them, that they are an animal. How do I get to know whether these they have some similarity? By just looking at the representation that they have right now. Because if you see the dot product example, that will explain you pretty well. Because right now we saw the representation of cat was 100, right? So cat has a representation 100. Dog has a representation of 010. You're finding the dot product of these and you're getting zero. Okay. Even if you find the dot product, I mean, suppose this is a vector and even this is a vector. So we're just finding dot product of vector. Dot product of two vectors gives the distance between the two vectors, right? Similarity between the two vectors. So if the dot product is equal to zero, which means there is no relationship actually between these two vectors, right? And even the cat and car has the same value, which is zero, which means all words are equally unrelated. So there is no relationship between words at all, right? Now, the problem, the solution to this problem now is dense vector representation. Dense vector representation can help you in solving the problems with the above approaches. High dimensionality can be addressed, okay, and sparse, again these issues can also be addressed, and similarity captured. Here no similarity was captured, but with the dense vector representation, all the above three problems can be very well captured. So we'll see what dense vector representation is all about. Fine. So what exactly is dense vector representation? Now, in the dense vector representation, the words that we have seen are represented as dense vectors in a continuous space. Now, two key terms that we notice here is dense vectors and a space, a continuous space. What exactly are those? Now, in this video, I'll just give you a very top discussion or top overview on how these vectors are actually calculated. Note that these vectors representation of these tokens are not randomly assigned. Okay, they are calculated using some set of procedures. So we have something called bag of word models, skipgrams, okay, or you can also use transformers to get embeddings. How do we get embeddings of words or tokens? There are three approaches, either a bag of words or the skipgrams or the transformers. You can calculate or you can find the vector representation of words using either of these three. Transformer approach is what is being used now, right? Because this is the latest innovations that we have, which gives us very fine quality embeddings, right? We'll understand why in a separate video. I'll be covering these about how the vector embeddings are actually generated. But now, just keep in mind the solution to all the challenges above that we see. How do we represent a word into a number form? How can we have a numeric representation of the words, right? The solution to all the problems above is a dense vector representation. We can represent them in the form of dense vectors. The key idea, similar words will have similar vectors. I mean, if you can find the similarity score between two vectors, and the similarity score will be very high if two vectors are very similar, and that itself will be very intuitive. Because if you see cat and dog, let me zoom it, the vector representation of cat using the dense vector representation is zero point 0.2, zero point 0.1, zero point 0.9 separated by commas, right? And for dog, you see the same, it's pretty similar. The vector representation is pretty similar, right? You see, The cat has a vector representation of zero point 0.2, zero point 0.1, zero point 0.9. Dog has a vector representation of 0.25, 0.015, I mean 0.15 and 0.85. And if you find the similarity between these two, it is high compared to the similarity between cat and car. It's way apart. If you see, cat has zero point 0.2, cat has zero point 0.2 here, but car has zero point 0.9 here. Cat has zero point 0.1 here, car has zero point 0.8 here, cat has zero point 0.9 and car has zero point 0.1. If you find the cosine similarity of these two vectors, they will be very low. I mean, the vector similarity between cat and dog will be high, and the vector similarity between cat and car will be low, which means the meaning is encoded geometrically. That's the very interesting fact about the dense vector representation of words. The meaning gets encoded, right? I'll also show this in the next video which I'll be creating about how the meanings are captured. Because if you see, words with similar meanings will be somewhere very close in the vector space, right? So if you understand the similarity right now, what it is basically we measure the similarity using the distance or cosine similarity. How do you find the similarity between two vectors, right? Say for example, I have vectors cat and dog, same thing that we discussed here. And these vectors are very close, indicating a semantic similarity because the similarity score, when you do the dot product between these two vectors, the similarity will be very high, right? The similarity score will be high, right? And hence it indicates that they are very similar to each other. How is a geometric representation? If you plot them in a vector space, you will find out, because if you see, for sake of simplicity, this is three-dimensional, right? You're representing a cat with points in a three-dimensional plane. You're representing a dog with points in a three-dimensional plane. It means the dimension size here is 3. And in a three-dimensional plane, right, if you visualize this right now, it is visualized in 2 dimension, but if you visualize in 3 dimension, the cat and the dog will lie very close to each other compared to car will be somewhere way apart. I mean, it will get a good distance from this because this belongs to a group animal, right? Hence somewhere it has captured this hidden meaning, right? That it belongs to the same family, hence it is closer in the space compared to car. You might find a vector for a bike somewhere near because it is a vehicle, right? So that's what is happening in the dense vector representation, and it's pretty interesting. We'll learn how this is formed in the next videos. So finally, what do we have is the embedding space. The space where vectors live is called the embedding space, right? Each dimension will capture some features, and we'll understand this. What is the dimension? So if I say for cat, I represented it as suppose zero point 0.1, zero point 0.2, zero point 0.4, right? So dimension size is 3. This is D1, D2, D3. Each of these dimension is capturing some feature of this particular word, right? Now, where do these vectors come from? So these vectors come from pre-trained models called word to wake or glove. Okay, even the LLMs can learn these vector representation during the model training, and this is a very important thing. I mean, most of us make mistake here. We assume that if you see the transformer architecture, right, we are giving some inputs here, and that input is getting converted to input embeddings. We might think that for converting the input tokens to input embeddings, we are making use of word to wake or glove models, right? Glove embeddings. But that's not true. Okay, if you do further research, you'll find out that these transformer architecture, okay, when we'll discuss about how the embeddings are generated by transformers, we'll come to know that it starts with an embedding matrix which is randomly assigned with some weights. And during training, right, during training itself, because you know how training works, it passes through all these, comes back propagation takes place, the weights are adjusted, and finally at the end of the training, the embedding matrix comes with very fine embeddings representation or the fine vector representation of the tokens, right? So it starts with very random weights, and these weights are adjusted finally to get the perfect vector representation of the word. So it does not uses word to wake or glove embeddings. Okay, it can use them, but it does not use. It has its own vector embeddings in place, which it comes up with during training. So that's how embeddings are actually generated. So modern LLMs learn embedding automatically. Okay, keep this in mind. So now, what was the full transformation pipeline from the words which can be understood by humans to machines? From here to here, to come from here to here, we first do tokenization. We convert these to tokens. Okay. Now, each of these tokens will assign a token ID, but it's not that we'll just rely on this token ID. No, we know that each of these has a vector representation, right? So the token ID will be mapped with the particular vector representation. Say 0, 1, 2. 0 has this embeddings, 1 has this embedding, 2 has this embedding, and 0 actually means I, 1 actually means love, and 2 actually means AI, right? So each of these has a vector representations. And right now, just think, for getting this vector representation, they are just using either of these models. Okay. But if we go for LLM training, we'll calculate it during the training itself. Now, why this matters? Because with vector representations, models can measure the similarity. We already showed you that if two vectors, the similarity between them is high, which means there is a similarity between them. For example, cat and tiger, cat and dog, there will be a similarity between them. But cat will be very different from car, hence the similarity score will be low. It learns the patterns, right? Hidden patterns can be learned because both cat and tiger belongs to a family. They have four legs, and all those hidden patterns we cannot imagine. Okay, and it performs some mathematical operations on language. It becomes easy, isn't it? We just now found out the vector representations. We can calculate the similarity, the distance between the vectors. Now, there is a limitation associated with this approach as well. There are words, example like bank. Right now, bank might refer to the river bank or the financial bank. How do you remove this disambiguity? There is no context awareness yet, right? Right now, the vector representation of this bank and this bank will be same using these vectors that we used here, right? But this can be solved. We'll discuss this in a separate video. But keep this in mind that language becomes computable when it becomes geometry. When you're able to convert these words, these tokens into vector representations, we are converting them to vectors means we can visualize them, and hence it becomes computable, right? Because you can find the similarity between the vectors, distance between the vectors, you can find the patterns between them. Now, this becomes interesting if I just take you through this particular web application. If you see, this is a embedding projector by project.tensorflow.org. Now here they have around 71,291 points. You can say that this is the vocabulary size, and see how the words are visualized in the vector space. If I type a word cat and set the number of neck words to suppose 5, okay, and then we just see how it looks like. You see, cat is the word here in this vector space, which has a dimension of 200. Remember, the dimension of this vector is 200, because when we were going through that particular document here, we were assuming for simplicity the dimension of the cat was 3, isn't it? 3, only 3, d1, d2, d3. But now what do we have is a vector of dimension 200. So which means there are 200 parameters using which a cat can be identified, 200 parameters using which mouse can be identified. And that's where you can find out the vector representation of cat, dog, mouse would somewhere be similar, and the distance between them is less, hence they come in a neck bud, isn't it? If I increase the number of neck buds, say if I say the number of neck buds to 50, so all the 50 neck buds that you see belongs to somewhere the animal family, right? Which means these hidden patterns are captured. That's the beauty of having the vector embeddings for these words or the tokens. Now, if you see a cluster somewhere far away, somewhere here, if I see, it randomly has some words which has no relationship between cat at all, right? If I see again this time not cat but car, you see car, and if the 50 neighbors of cars are like where is it car? Okay, car, caravan, and the word with prefix car are also coming in place, right? If I say bike, see, bike, bikes, super bikes, and there are more beside this, isn't it? Motorbikes. So that's how you can play with these and actually, try to understand how vector embeddings helps, to make things pretty clear, capture the hidden patterns between different words. That helps us to find out which family they belong to. Because just by looking at the cluster, you can identify it. So I hope this discussion was quite helpful. So in the next videos, we'll be discussing about the points that we discussed. That is how the vector embeddings are calculated using CBOS, skipgrams, and also the most important priority discussion for us would be in transformers. How does transformers itself generates the embeddings? So that's it from this video. Thank you.